Good morning, folks. This is Todd Coburn of Cal Poly Pomona with Lecture 7 of Arrow 4080. Today we're going to look specifically at how to handle symmetry and when we have inclined supports. Let's see how that works. So symmetry is important. We see that in our everyday lives. We kind of hope that we're symmetric. Every time I look in the mirror, I wish I was a tad more symmetric. We generally avoid being non-symmetric. This guy looks fairly symmetric, but I don't think I want to look like him. I don't know about you guys. This one looks symmetric. That's probably why we all like her so much. This one looks fairly symmetric, and you see there's some differences. Still looks pretty good. This one kind of off a little bit. And this one, quite symmetric. I'm sure that's what we're all attracted to. Structures are people too, and symmetry matters. Let's take a look at how that looks. So here we have a structure that we can go and analyze. This looks like we have truss elements. It looks like we have 1, 2, 3, 4, 5, 6, 7, 8 different members on a 2-node structure. And we can easily write a finite model or even write a matrix, system of matrices to solve this, write the stiffness matrix for each. But if we're doing this by hand, we see this is going to be rather large. Since it's rather large, that's going to make it difficult to solve with our hand calculators. But if we notice that this is symmetric, both in geometry and in properties and in materials and loading, then we see that we can actually simplify the problem, make it a little more solvable. We do that by identifying the plane of symmetry. The way we do that is imagine holding a mirror. We all kind of want to be symmetric about this kind of axis, but not about this kind of axis, right? So we hold a mirror and see if we have symmetry. If we do, if the structure looks the same in geometry, properties, material, and loading, then we can break it up at the interface, and we're going to tweak it a little bit so that it becomes a reduced problem. So this guy here, we can identify our plane of symmetry and identify it like this. In this case, we're looking at only the left half of the structure. We're going to impose boundary conditions at the interface, and we're going to adjust our loading at the interface. Okay? We're going to look at this a little more in just a moment. Now, this aircraft, is that symmetric? Is a good question. A lot of times aircraft are fairly symmetric from the left and right sides, and for that reason a lot of times they're only analyzing half of the model, or at least they used to when we had more computer problems with solving these large matrices. So let's take a look at how this actually works. So let's go back to this little structure we saw and try and figure out why we were able to break it up the way we did. Here's some different types of structural symmetry, and mainly we're going to be looking for this reflective symmetry, as if there's a mirror there, okay? When we do that, we're going to find, we have to recognize first that there is symmetry. We're going to need to remove one symmetric part, and then we're going to impose constraints for the part that we removed, much like drawing a free body diagram, and then modify the loads on the interface. We'll do that step by step in the next example. So here's a little example. We've got a truss. This is the same problem, and we're trying to find our loads and everything else. Okay, so we take a look at our truss. Here it is, and we look for a plane that if we slipped a mirror there, that it'd be the same on both sides in that mirror. Okay, so when we do that, we identify our plane of symmetry. It looks like we're symmetric about that line. If we had a mirror there, it would look the same on both sides. So we're going to redraw one half of this up to the boundary. That's what we've done here. And then what we're going to do is impose our constraints to simulate what's removed. Now, since this is perfectly symmetric, whatever happens to the left side has to happen on the right side. That means this can't move this way or this way because it's symmetric, so it responds exactly the same on both sides. For this reason, we can replace all this structure up here at this interface with a roller support, allowing the structure to move up and down, but not into the wall, into the other part of the structure. Same thing, that's at node 2. We see the same thing at node 4. We can put a roller support there, and at node 3 down below. We also will take the loading, since there's one load applied on the plane of symmetry, we will divide that load in half, so it becomes not 2p but 1p. We now have a brand new structure, and we see we only have 5 elements and 4 nodes. This is going to make this a lot easier to solve by hand. Once we get to this point, we solve the structure as we did before by computing the local stiffness matrices, converting those to global stiffness matrices, putting into the large global stiffness matrix of the entire structure, and then imposing our constraints. In this case, with our modified structure, we're going to have constraints in the x and y direction at node 1, and at node 2, 3, and 4, we're going to have constraints in the x direction but not in the y direction. Okay. Now, if we have an inclined, so symmetry, as long as we can recognize it, is fairly easy to handle. Got that? Now, symmetry is fairly easy to handle, as we see here. The hardest part is recognizing symmetry and not assuming something symmetric that's not, because of the challenges with identifying symmetry correctly. Sometimes it's easier, especially if you're using a computer, just to solve the full structure rather than take a chance on making a mistake on identifying that symmetry. However, we can simplify our problems as long as we carefully check our model and make sure that we truly have symmetry, and we properly impose our boundary conditions. Now, the next idea we have is inclined supports, and when we have an inclined support, that's going to be a little more challenging because our constraints change a little bit. Okay, this is not too difficult either, but it is going to be a little more complicated. Are you with me? All right, let's say that we have a truss and we have an inclined support. We see at node 3, so we see at node 1 we're constrained in the 1 or 2 directions, but at node 3 we're only constrained in this local y prime direction. We're not constrained in the x, we're not constrained in the y, we're constrained in this other coordinate direction. This is going to make it a little challenging to impose the boundary condition. So here's how we're going to handle it. Okay? We're going to have to transform our information at that inclined support into a local coordinate system. From the current to from there and back again. In fact, this is what Bilbo was actually writing about in his book there in background. Again, he really wasn't intending to talk about orcs and elves at all. He was trying to do structural analysis, but being a hobbit, he messed it all up and covered his error with fairy tales. So we're going to have to transform there and back again. Here's how it works, okay? So if U3 and V3 are our global displacements, we can use the transformation similar to what we've used before, where alpha is just the angle of that inclined support now, to get our local coordinate deflections U3 prime and V3 prime, okay? We're going to define this as T3 at the node. This is our little transformation at that node, okay? And because of that, we can write this more generally, that our local displacements are equal to this transformation matrix T3 times our global displacements at any node, okay? That's at any node, but only at the inclined nodes. All right. Now we look at that, we say, yeah, but only 3 is transformed. 1 and 2 are not transformed. And recognizing that the identity matrix will not change the element at all, we can remind ourselves that the identity matrix is shown like this, and we notice that if we multiply any deflection of any other node by this identity matrix, then we won't modify that node at all. So what we're going to do is come up with a transformation matrix that transforms the nodes that we need to transform and that leaves the other nodes alone. This means that our total transformation matrix, to account for the inclined and uninclined nodes, is going to be, we're going to call it T sub r. We're going to use the identity matrix along the diagonal except at any node where it's inclined. So if node 1 were inclined, we would imply T3 at node 1, but it's not, so we use the identity matrix. If node 2 were inclined, we would put the T3 at node 2, but it's not, so we're going to have the identity matrix. At node 3, we actually have an inclined support, and so we're going to apply our T3. Now notice T3 is the T for node 3. If we hit inclined 1 or 2, we would use the angle of that incline at those, and we would have called that T2 or T1 and placed that in the appropriate place. Got that? Now that we have this transformation matrix for the whole matrix, for all nodes, we can use this mother to transform our global stiffness matrix. So we're going to take our global stiffness matrix, we're going to pre and post multiply it by this T sub r, and this will give us the transformed global stiffness matrix. Now we're going to need to use our old global stiffness matrix and the new global stiffness matrix, okay? So what we're going to do now is use this. We can now reduce our matrix in the same way as before, right? We can also transform our deflection. So we're going to use this global transformed stiffness matrix with our displacements to calculate our forces, and we're going to also use the regular global stiffness matrix with our displacements to get our forces. We're going to see how that works in a minute. We can also transform our deflections at any node. You'll notice the forces. The forces at node 3 are going to be this T3 times the global forces in node 3, right? Now, the local forces at node 2 will be identical to the local forces at the global forces at node 2, because that identity matrix is the T2 is the identity matrix and T1 is the identity matrix. Do you see that? All right. So let's summarize our method now. And I'm marking everything green that's unchanged. We're going to model our system with nodes and elements. We're going to determine the local stiffness matrix for each element. We're going to determine our transformation for each element. This is the old transformation matrix we've been using, T2 star. We're going to transform our element stiffness matrices into a global stiffness matrix as we did before. We then are going to construct our global stiffness matrix in the same manner as before. Here's where we start to insert new ideas. We're then going to calculate our transformation matrix at each inclined node. So in our previous example, T for node 1 was just the identity matrix. T for node 2 was just the identity matrix because neither was inclined. Node 3 was inclined, so we calculate, using the angle of the inclination alpha, we calculate the transformation matrix for node 3. And this is what it is. We then construct our complete transformation matrix by combining T1, T2, and T3. Remember, T1 and T2 are both identity, the identity matrix in this case. That gives us TR. We can now transform our global stiffness matrix into a transformed global, and we can impose our boundary conditions. This will become clearer when we get to our example in a moment. Once we've done that, we're going to solve our system of equations, the reduced system of equations, to get our unknown forces, right? Or using our forces, our external forces, to get our displacements in that reduced, transformed direction. We then can transform this is a global local set of stiffnesses, and we can transform that to a completely global set of displacements by pre-multiplying by the transpose of that transformation matrix. We then use our global displacements to determine our global forces, okay? And our transformed global matrix to get our transform forces. So we're actually going to do this twice. You'll see we're going to put in those global coordinates, all global coordinates, with our global stiffness matrix to get the global external forces. This will give us any reactions at non-inclined nodes. We then are going to use the local, or it's going to be DG prime actually has some uninclined information and some inclined information. We're going to use that and multiply that against kg sub t, and that will give us the inclined global forces. That with when we calculate F sub G, we're going to look only at those forces that are in global and not inclined. When we look at FG prime, we're going to look only at those ones that are inclined. And those are going to give us all the forces that we need. We then can go and take the forces that are appropriate for each and every node, the global forces, and transform them or pre-multiply by the global stiffness matrix to get the global forces of each node, and then transform the local coordinates as we did before. Got that? Let's see how that works. So here's a little example with an inclined support. Okay, we see 1 and 2 are not inclined. Node 3 is inclined, so we're going to need to transform that. We can calculate the angle of the incline if that's not given. Looks like the angle is given. It's a 45-degree angle. Okay, so we're going to go ahead and solve this puppy. First, I like to echo my input properties, my nodes, and my connectivity information. We then calculate our global stiffness matrix for each. This is the standard way we do this, right? This means we calculate the local coordinates, the local stiffness matrix for each element, and then we transform that by T2 star to get the square one, to get the global stiffness matrices. We then assemble our global stiffness matrix. That's what this is. We then are going to transform that. First, we need to calculate our transformation. We'll see that T1 is going to be identity, T2 is going to be identity, and T3 is going to be this matrix shown here where we put in alpha's 45 degrees. We then construct our capital T sub R, which has the T1, T2, and T3. You can see there, but T1 and 2 are both identity. We multiply our Kg by that using the relation I gave you, and that gives us our transformed global stiffness matrix. This is here. Now you'll see that anything dealing with node 3 is potentially modified now. Okay? We now have two matrices. We've got the global and we've got the transformed global. Okay. We're going to use the transformed global, and now we're going to impose our boundary conditions. At node 1, it's fixed in both the x and the y directions. At node 2, it's fixed in the x and the y directions. At node 3, this is, remember, the transformed global stiffness matrix. At node 3, it is free to move in the local x, but it is constrained in the local y. Since we have modified this, those first two were node 1, now we got node 2, and then at node 3, you'll see we have just removed the y direction, the local y direction, okay? If we redraw this, we see where these four elements. We're going to get the, out of this, we're going to get the displacement at node 2 in the x, and we're going to get the displacement at node 3 in the local x. So we're going to take our forces that are applied. We see here, we have what? 1,000 kilonewtons in the x direction at node 2, and we have no other forces on the structure. We have displacements now. We now can go and solve this with those forces to calculate the two displacements we don't know, the x direction at node 2 and the x prime direction at node 3. So we perform that multiplication and we get the transformed displacements. This gave us the global displacement at node 2 and the local displacement in the x at node 3. Okay? We can now take those displacements, multiply by the transformation matrix, and get the global displacements. You notice when we do that, that displacement in the x at 2 did not change, but the displacement in the inclined direction at node 3 in the u prime direction changed into now two components for the global x and y. We can now multiply that by our Kg transformed in order to get the global forces. And now we see we have the global forces at node. We get that constraint force at node 3 in the v direction. Got that? Okay. We then can take our global displacements and multiply them by kg, and that gives us everything else. Now you'll notice the only difference between these two matrices, these are identical, except in the first one, we have those inclined values at node 3, and the second one we have the global values at node 3. We then can use the global displacements with our global element stiffnesses to calculate the global forces, and then transform those in the normal way into local coordinates. Make sense? So that's how we handle symmetry, and that's how we handle inclined supports. This is maybe one of the trickier parts of the lecture, and you're going to want to make sure you take your time with the homework to understand it. That's all I got. Thanks. Bye.